Okay, but yeah, welcome back to the formal methods lecture, formal methods for software engineering. And we're still looking at satisfiability modular theory. So we will have another overview of some like puzzles and applications, and we will look at a bit more advanced encodings. Because the thing is, now we have this language and this tool, and we can solve problems, but the question is, how do we best solve them? Or maybe are there differences in trying to solve them? We have this satisfiability modular theory, so we could use different theories to solve the same problem. And we're going to look at some example where it's actually possible to use different ways to solve the problem. So this example here, it's a small puzzle. So yeah, the question is, why do we always have stuff like puzzles in in computer science in general, or in formal methods? I think the idea is that the puzzles are boiling down some problem that you might see in the real world, but it simplifies it in a way that everybody can easily understand it, right? You don't have to take it with domain knowledge to understand these kind of puzzles. So yeah, let's look at this one. So this could be some, for example, allocation constraint of, I don't know, resources to hardware or something like that. But here it's phrased as a puzzle of 3 houses. And then there are 3 residents of these houses. And one of them is a math major, one is a computer science major, one is a philosophy major. And now we know that the philosophy major lives directly to the right of the red house. We know that the computer science major lives in the blue house, the math major lives in house 2, and we know some, well, further things. So the houses all have distinct colors. The colors can be red, white, or blue. And the residents, well, they can be mathematicians, computer science students, or philosophy students. And we want to figure out, based on these things that we know, and based on these rules of the world that we are trying to model, who lives where. So that's basically the task. Yeah, and how do we do this? So this is some, well, illustration. We have house 1, 2, and 3. We have those, well, different subjects. What do we say? Computer science, math. This could be math. Which one is philosophy? Doesn't really make sense. Well, which one is, maybe this one is philosophy, staring at the matrix. And, well, computer science, and what was the other one? Math? Maybe that's one. That doesn't look like math. Well, that's a library. It's a library. So math, yeah, makes sense. Okay, so we have math. No, we said this was math. Wait, so then is this one computer science, or, yeah, well, philosophy goes to the library. Great. All the stereotypes. Yeah, okay. So now how do we allocate this? We know there are some constraints, and the constraints are up here. So we could be lucky and just try it out, right? Or we try to encode this. One way to encode this would be with Boolean variables, right? And this would be one attempt where we say, well, we could say that house 1 is blue, house 1 is red, or house 1 is white. We could say that house 2 is blue, red, white, house 3 is blue, red, white. House 3 has math, computer science, philosophy. House 2 has all these, right? And then this is one way where we really just use propositional variables, which means that we can also do this with a SAT solver. But that's fine, because our SMT solver basically also can do all the SAT solving. So this would be the encoding of the variables. Now the question is, how do we write the assertions, right? How do we write the kind of these things that we know? The philosophy major lives directly to the right of the red house. That's probably a very tricky bit. The math major lives in house 2. So this math major lives in house 2. this looks like it's exactly this one, right? So we can have an assertion. So let's say we can simply assert H2 math. Okay. Then what else do we have? Computer science major lives in the blue house. How do you do that? So, well, we can say, and now the question is, what can we express in this, let's say, vocabulary that we build ourselves, in the model that we're trying to build here? Our model will have, well, variables that are true or false. It will assign true or false to all of these. So can we express, based on constraints on this model, that the computer science major lives in the blue house? I think, let's just assume it's house 1. How would we express that the computer science major lives in the blue house, which is house 1? We would maybe make an assert, right? And then H1CS and something else, right? So he lives in house 1, and house 1 is blue, right? Because he lives in the blue house. So we can also say H1 blue, right? But that's not the only possible solution, right? Could also live in house 2. So we could, and then we will see how to combine this. No, I didn't copy. Let's try that copy and paste again. Okay, so could also be that it's in house 2, or house 3, right? Yeah, could be. Now, how do we connect these? Because right now there's no operator connecting these 3, right? We could put an OR. Yeah. Let's try that. Maybe we're lucky. Why is an OR dangerous here? I think like yeah, checks. Ah, wait, that's So now we have a computer science student lives in house 1, and lives in house 2, and lives in, well, do we have H3 CS? Where was H3? H3 CS. Okay, well, the computer science student only lives in 2 houses. That's not so nice, right? There's something wrong. So we probably don't want this OR. We want maybe like an exclusive OR over these 3. I think we can't just write XOR. I think that's not in SMT. Let's try. I guess it's not. Did that work? Really? Well, now that something worked, we're not sure that it has the right meaning, right? Let's check. So H1CS is false. Where's H2CS? H2CS is false. Okay, so maybe we have an XOR. Good. Do we trust this? I don't know. So do we also have H3 blue? Yeah, looks kind of fine, right? But actually, this doesn't rule out that any of the other houses is not blue, right? So how do we rule that out, that none of the other houses is blue? Well, we just found the XOR, right? So we could make an assertion. And that is a very, very, let's say, different kind of constraint, right? These two constraints, they are the ones that we got as clues from the puzzle. The constraint that only one of the houses is blue, that's somehow different, right? Because that is a constraint that we kind of get from the background knowledge about how this puzzle works, that we can only assign this blue once. So yeah, let's say only one house is blue. How do we say that? Well, we have H1 blue, H2 blue, and H3 blue, and then we said very likely this XOR works, right? So not so bad. And well, only one house is of each color, right? Actually, this is not only supposed to be true for blue, this is also supposed to work for the other colors. So what other color did we have? I think red. And then, well, white. Okay. Well, so that's making sure that really the houses, only one of them has each color. And this XOR also makes sure that each color is used once, right? So we're making sure multiple things. We're making sure that the color appears because it's an OR, and it's exclusive, so we're making sure that it appears only once. So that's actually quite nice that we are already encoding not so trivial constraint about the colors of the houses. Do we have something similar? We have these majors, right? So only one house, well, of each major. So actually here, can I do a search replace only in selection? How do we say only in selection? Match case, mutual word. No, well, actually I wanted to. Well, it's probably faster if I just type it. Okay. Did I spell this correctly? Yeah, CS. Then what did we have? Math. And then we have philosophy. Okay. Well, not so bad. Now we have made sure that each house has one color. Each house has exactly one kind of student, and the student is distinct between each of those houses. So now the only thing we didn't encode yet is which one was it? The first one, the philosophy major lives directly to the right of the red house. Okay. That sounds like, well, let's see. Yeah, how do we assert that? There are now, I think we have had a very, very similar pattern, right? We had this pattern where we said, well, computer science student lives in the blue house, so we just listed all the possibilities. So what are all the possibilities for assignments where the philosophy major lives right of the red house? So let's say the philosophy major lives in house 1. Does that work? Not really, because if the philosophy major lives right of the red house, then, well, there's no house 0 in our setting, so house 1 doesn't really work. So house 2 might work. And then what do we know about house 1 if the philosophy major lives in house 2? And we know that house 1 is red, right? Because and then we have another option that the philosophy major lives in house 3, and then house 2 must be red. Yeah, and that's about all the options. And then the question is, what operator do we use to combine this? Yeah, let's use this newfound operator. Great. Let's now and then check for satisfiability. Looks like there's a lot of stuff true in the beginning. So, are we done with all our constraints? We have encoded the variables about houses and their colors, the majors living in the house. Then we have made sure that these colors, you only get one for each house, and you get exactly one, and then here also exactly one major for each house. This sounds quite, quite good, and we're still satisfiable, right? That's great. So despite these constraints, it's still satisfiable, which means that well, there's now some solution. Now, how do we get the solution? How do we actually now color our houses? Well, we just look what's true in the model, right? So the model says that house 2 has the color blue and the philosophy student lives there. And house 1 has the computer science student and house 1 is also blue. How can this also be blue? Maybe this XOR is not what we think it is. That's okay. Maybe these things are not like sums that you can feed them with as many parameters as you like. Maybe we made some mistake here. Let's try that. Well, H one blue. Let's just check if that's no. Well, there was another constraint that I wanted to use here. Let's see if that one works better. If we look at the tutorial of SMT-lib, then under propositional logic, we see actually what kind of operators there should be and what we can use. There's some like cardinality constraints, at least 2, and then you give a set of Boolean variables that should have at least 2, well, 2 of them true, or you have the at most. So at least and at most are not really working for us, but there is this pseudo-Boolean constraints, and this actually is you can put weights to the assignments of Boolean variables, and then you can say that the sum of the weighted values of these variables should be a specific number. So here we're saying that this pseudo-Boolean, well, GE, that's, well, I'm not sure what the GE stands for, probably for something equal, greater or equal. So here we have at least. Now we have at most, and we also have the equals. So we probably want the pseudo-Boolean equals so that the weighted sum of them then equals, well, for us 1, because we want to pick exactly 1. So let's now use this method PBEQ. That's a bit more tricky than the XOR. So Let's try to do a search and replace. So every XOR we want to replace with this pseudo Boolean equality, and then let's just check what elements do they have in common. They all have the next value also in common, right? We also want them to be the sum always to be exactly 1. And then they also have all the other next values. We weight, what are the weights that we would assign to each of these Boolean variables? So if the Boolean variable is true, then we sum up exactly the weight, and if it's false, then the weight is like multiplied by 0, right? So what weight do we want to assign to each of them? We want the sum to be 1 in the end. So what are the weights we should assign to them? If we want the sum of the weights to be 1 in the end, then, well, probably 1 is a good weight for each variable, right? So we want 1, 1, 1. And I think that's about the commonalities that we have. Then we just close the, well, first parenthesis. Then we list the variables, and then we need to close another parenthesis, but that's now a bit tricky. Yeah, let's replace all of them. And now we're missing some parentheses. So, oh. Right? No? We were not missing them? Because we had the closing one of the XOR anyways. Yeah, okay. Okay. Oh, and this one, okay, this one is a bit tricky because this had basically 2 Boolean expressions here. So now we are expecting 3. It's not quite right. This one was also, I think, just 2. Yeah, now let's check. It doesn't like something. Function expects arity +1 rational. Parameters line 41. How many parameters did we have? Oh, we had 3, sorry. Yeah, this was one where we had 2. I just didn't see this one. Yeah, it was hiding. And here we have, yeah, we have 2. Let's run that again. And let's check again, how many blue houses do we have? Everything false. Right? Did we have any? House 2 would be red. What do you see that? House 3. Let's look at the colors. We have house 2 red. Now, this stuff is not really readable, right? Where's house 1 white? Here. Okay, and that's about the colors. So the colors now make sense, right? So this means our new fancy XOR doesn't really work, right? Or we're not sure how to use XOR. But usually XOR means exclusive, right? So yeah, so don't use XOR now because, yeah, I didn't know it existed, and maybe it means something different. Maybe it's some different implementation. So what you can use is these pseudo Boolean constraints, and the one that's really, really handy is this one where we just say this equality. We want the sum of these to be added up as some specific value. Yeah. So now how do we go on further? How many other truths do we have? So we had H3 has the philosopher, and H2 is the math, and H3 is the computer science, right? So, wait, which one had the philosopher? H3 had the philosopher. And where else? That doesn't work, right? Can't have the computer science students and the philosopher in the same house. So what did we do wrong? H1CS. We say that, wait, this has to be exactly 1. No, we say it has to be exactly 1, right? But now what could be is that in every house we have exactly 1. So each major only lives in exactly 1 house. But we never said that each house only has exactly 1 major, right? So what we're missing is we actually need to say only 1 house. Well, that's actually only half of the story, right? We also need to encode some more. We need to say that house 1 has exactly 1 major, right? That gets really annoying. But that's kind of expected because we are doing something very, very low level, right? We are only using propositional logic. We're not exploiting any of the strength of SMT solvers with all the nice theories that they have. So now that we have this, we can kind of guess that we also need the same thing for the colors, right? Because they are very similar. We just said that we are here assigning each color to some house, and we're not assigning that color to multiple houses. But could it be that we have house 1 blue, house 1 red, and house 1 white? We only want 1 of them, right? So so we had this very nice idea of, just encode it in Boolean variables. So let's check again. Now we have, let's look at the colors. House 3 is white. House 1 is blue. House 2 is red. Well, now let's hope that no other colors appear, right? Because that's about all the, false, false. Great. Okay. So now let's look at the majors. We have the computer science student in house 1. We have the philosopher in house 3. And H2, the math. Now let's hope that there are no further. Great. Now we should go and check all these constraints that we wrote down on the bottom. Did somebody check already? These constraints? Did we have math and H2? Well, we must. That's like a given. Otherwise, this assertion wouldn't really hold. So I think we can. Well, probably. These were the kind of encodings that we had. There are different encodings. We could also have done it with implications that if house 1 is blue, then the computer science student must live in house 1, right? There are different ways to express this. And then we need to encode. This was actually the even worse bit, right? These constraints here with the red house of the philosophy major, this is actually quite straightforward, right? Those were the lines on the bottom. We encoded them slightly different, but these were just 3 lines, right? This is the tricky bit, the bit that gives us the clues about the system. But then this is the bit that we struggled a lot with. Every house has a color, every house has a resident, a color can only be can't be on more than one house and can't have more than one resident for each house. So this is the stuff where we had these long blocks of well, you can't be here, you can't be there at the same time, stuff like that. This is the tricky bit. And after we also encoded those, because before that we saw when we didn't encode them correctly, we get some very strange settings that as a human we would see, well, this can't be true. If house 1 is blue, it can't also be white. Or if one major lives in house 1, then the other major can't live in house 1 as well, right? But the SMT solver, we have to give it all these information. So now this should be a possible solution. I'm not sure if there are multiple ones. And we used here those pseudo-Boolean constraints. We used this pseudo-Boolean equality constraint, which is, yeah, quite nice. Now, what other encodings could you think of? Because this one, I don't know, who liked this encoding? And what were the problems with this encoding? So first of all, we have tons of variables, right? How many lines of code does this thing have? Or how many lines of model or of spec? Well, it's 56 lines, so that's also quite long. I mean, it's probably longer than the homework. Yeah, I'm quite sure, right? Well, the last one might be a bit, yeah, not sure how long this is going to get. Okay, but yeah, we have, I don't know, too many variables. Then we have these strange constraints that just tell us something about the relation between the variables that might be much simpler expressed in some other way. Probably, could be. Yeah, and then these things here, they were actually not so bad, right? I mean, well, this thing, the math major lives in house 1, house 2. This is exactly a single statement, right? A very simple statement. And these ones here, well, yeah, maybe we could make them a bit easier. But the question is, how would we do this? What are possible other encodings? Do you want to put them here, or do we just, let's just, yeah, discuss what are possible other encodings? Does this remind you of some similar stuff that we did before? We had this Agatha puzzle, right? And this Agatha puzzle also had relations between things, right? It had relations between people. It had this richer relation, the hates relation, and the killed relation. Those were relations between people. Here we have, well, also relations between things. We have relations between, well, houses and people, and houses and colors. So maybe we can do a similar encoding. So in the Agatha puzzle, we used data types, right, to represent the things. And then we used those functions or predicates to give us the relations between those things, right? So we could have some data type for maybe the houses, some data type for the majors, and some data type for the colors. And then we could use relations between those data types and encode the constraints only in terms of those relations. So maybe that's another way. And then there's even more. So yeah, can anybody think of another way to model this? So what were our variables in the first encoding, in this Boolean encoding? They were just propositional variables. And they couldn't really relate to any entities. The variables, they were just expressing relations already, right? If the variable is true, this means a relation between two entities holds. A relation between a house and a color holds, or a relation between a house and a major holds. So this is a very, let's say, indirect encoding. We're not really encoding the entities. Then with data types, we give we explicitly express, well, there are houses and they have these numbers, and there are colors and they have these names. So let's look at that one. So this is the possible encoding. We can say, well, we have colors and we have majors, and then we can relate them. So yeah, let's look at the solution directly, and we will see that wait, this is the let's okay. So we basically defined these colors, and then we need to relate them somehow to the houses. So there are multiple ways we could do this, either with predicates, or we can do this with variables, and we can simply say, well, there's a variable that holds the color of house 1. Right, so we could say house 1 color equals blue. This is then that this variable has the specific value. So should we do that? Should we say the math major lives in house 2? So how do we do that? We say the variable that holds the major of house 2. So has a certain value. So we could say, well, h2 major has the value math, right? Because that's the math major. So this one would express that we kind of assign to the variable of the major of house 2, we kind of assign the value math. Great. Then how would we say that the computer science major lives in the blue house? We could again list the options, right? Or we can use this implication that we had that we saw in the previous solution. So we could do another assertion where we say, well, basically we can say implies, and what implies what. So if h1 color, well, that's if the color of house 1 is blue, this implies that house 1 major is CS. Okay, and then we have a few other ones, right? Depending on which house it actually is, because this has to hold also for house 2 and 3. Okay. Yeah, and then this, we do it very, very similar again. The philosophy major lives directly to the right of the red house, right? So that's probably some, you can write it as implications again. So we would imply, so if now, well, we said, well, let's copy the lower ones. We said that there are some possibilities. Well, let's. So if H3 color is red, then H2 major is philosophy, right? So if H2 color is red, then H1 major is philosophy. What was the name? Yeah, okay. And H1 color red. This can't be, right? Because then there's no way to wait. It says the philosophy to the right of the red house. Yeah. So actually, so then we have H2 major is philosopher, right? And then here H3 major is philosophy. And if that one is red, there's no way to live to the right of it. So we can simply say, well, this doesn't exist, because that would not allow the philosophy major to live anywhere. That's of course not some operator. I think it needs a space there. Yeah. How about this model? So looks like we have lots of white houses, right? They all live in a white house. All the houses are white. Huh. What did we do wrong? Is there anything we said about the color of houses? We didn't really say what should be distinct. Wait, how do we express this distinct thing? Was it a keyword? Was it? Okay, and then we list the colors: blue, red, white. Okay, that's a good thing always to do. I wonder if that also works for variables. Right, so it's good that we say that these values of the data type, they are distinct. But I think we should also say that the variables are distinct, right? We never encoded the rules of the world that each house, like the two houses can't have the same color, right? I have no idea if we can do this with distinct. Let's try this, if that only works for... I'm not sure what the meaning of that is for variables. White, blue, red, that might work, right? So then we're also going to use that for majors, right? There was a... Okay, so now we have computer science, philosophy, and math. So let's, I mean, now this model is much smaller, right? The model is much easier to read than our previous model with tons of Boolean variables, right? So now let's check the last one. Does the math major live in house 2? House 2 major math. Sounds good. Now this one, the computer science major lives in the blue house, whereas the computer science major in house 1, and house 1 is blue. Great. Then the philosophy major lives directly to the right of the red house. So the philosophy major is in house 3. This means that the house 2 must be red. Great. Yeah. Okay. So this encoding looks nicer, right? Yeah. First two. See what happens. They might be implied because the variables must have distinct values. Okay, so yeah. Are you sure that the data type is already making it distinct? Okay, good. So yeah, anyways, they would be kind of implied by making the variable values distinct, because you can't have well, 3 variables of the same type with different values if you only have, well, less than 3 values. So they must also be distinct. Great. Yeah. So this is also in terms of length. How long are we? Well, we had 56. Now we have something like 29. Okay, so that's better. What was the kind of trade-off? So it was now much easier to say that we don't have the houses have unique colors, right? And it's also much easier to say that each house has a color, because simply the data type only has values for colors. So there's no other way than to assign some value to the variable, right? So we kind of implicitly set that each house must have a color by declaring one variable for each house, right? So there are some things now, because we used a special data type, we don't have to take care of these complicated constraints anymore. Okay. Then this one here. And this one here, well, we could still write them in one line, right? We could use this and the pseudo Boolean constraint that we had before. This would be the same, but still, these constraints, they look slightly complicated. And why is that? Why are these constraints a bit more complicated? Is this related to our choice of encoding? Well, probably it is, right? So what's the thing we would actually, let's say there would not be just 3 houses. Let's say there would be 100 houses. How would this thing change? This constraint say that the philosophy major lives directly to the right of the red house. Now we have 3 houses, we have 3 lines, right? Because we always need to say, well, if the philosophy major lives in house 3, then actually the red one is house 2. And this, if it's in house 2, then the red one is house 1. So we have some like order relation here, some relation that sounds like we want numbers to express this, right? Because if we simply say, well, this simply means that if the philosophy major lives in house n, then the red house is house n minus 1, right? So maybe we can try yet another encoding where we try to exploit these integers, right? And here, what about for this constraint? If we say that the computer science major lives in the blue house, so if we say the blue house is house K, then the computer science major lives in house K, right? So maybe we can do another encoding where we use integers instead. And this one is the data type one, and now this one is the integer one. For each color, we could say which position of house this color is basically associated to. So the red house could be some integer number, right? And then how do we say that the where did we need the red house? Yeah. Philosophy major lives directly to the right of the red house. So how would we express this now? So how do we say, where does the philosophy major live? That is this number, right? So, and what is the relation of this number with the red one? So if we say that the philosophy major is, well, n, then what does that mean about the red one? Oh. So the red one minus 1 is, well, isn't that then the other side? If we have the red house and we go -1, yeah, I think we should have a +1, right? Because if we want to the right house, yeah. Okay, good. Then how do we say that the math major lives in house 2? Well, that's now very easy, right? Simply math is 2, right? Good. The computer science major lives in blue house. So the value of the house where the computer science major lives and the house which is blue are the same, right? Should we try to run this? Okay, so the red house is house -1. Huh. Not what we wanted, right? How many houses do we have? We have house 0, 1, -1, 2, 4 houses now. Yeah, so we actually need to do some assert that we say, well, we want this kind of nice power of integers, but we don't want all of them, right? We want yeah, so we can basically say greater than, well, red is, well, greater than 0. Should we say greater or equal? We want them to start at 1, right? And then what else do we want? 3, right? Let's say if that works for red. Now red is a reasonable fun number, but all the other ones are still messed up. So how many do we have? We can put AND statements, yeah, but that's implicit. Well, that's, yeah, that's a lot of statements because we have to get these domains right. Okay, now is math, the math major lives in house 2. Great. Then does the computer science major live in the blue house? We have blue is 1, computer science is 1. Great. Do we have that the philosophy major lives, where does the red house is number 2, then the philosophy major should live in 3. Yeah, great. Okay, so, well, we had more lines. Well, we could have added, right? I mean, this thing up here is just, well, you could write this all in one line, I guess, or maybe one line for each variable. Doesn't really matter. So I think that we now have 3 different encodings. They all give us the same solution. And they're all quite different. So if you would rank those 3, who thinks the first one with the data types was the best? Best out of 3? Worst out of 3? Like by a show of hands, how many of you think it was the worst? The Boolean ones. The Boolean one. Okay. The data type one. Where would you rank this one? Best? Worst? Second? Okay, and which one is the best? The integer one? Okay, I mean, well, the question is always, we have to think about these multiple things that we need to express, right? We have always well, this step we have to build the variables which encode the problem. This was always easy, right? It was even easy for the Boolean ones because that's just, well, you just think about how to do it and then you just write them down. Then you have to encode the constraints of the problem. We saw that this could be different. So the Boolean one, our constraints, they had to be a little bit longer formulas, right? And then for the integer one, they were really the shortest, right? They were just very elegant. Well, computer science equals blue, and that's it, right? For the data types, yeah, they were also maybe fine. But then part of the constraints are not really just the constraints of the model, but also the constraints of the world that this model lives in. And this would be that each house can only have one color and stuff like that. And this was really, really, yeah, horrible, let's say, with the Boolean variables, right? We made tons of attempts to get it right. And we still, well, in the end, I hope we got all the constraints, but this was really the most difficult one. The data types was okay, but the integer one, I mean, what are these constraints? They are basically extremely simple, right? There's maybe, yeah, maybe there's even a subset data type of integers. Maybe you can define that, and then you're fine. Okay, so here I think they all have their let's say benefits. What's the benefit of the Boolean one? Why would you ever use that? Nobody would use it? Okay, so actually there are many like, let's say, products and real tools that prefer the Boolean ones, although they have to generate a lot more constraints. And the reason is simply that if you only have propositional logic, you can use a SAT solver, or you can use the SAT solving engine in the SMT solver. So those tools, they might still use Z3 as the backend, but still they only use the propositional logic of it, because then they know that Z3 only internally runs the SAT solver and never has to invoke a theory solver. The problem with theory solvers is that they're sometimes really not so easily predictable. Often they have issues with undecidability or issues with well, heuristics and running times. So SAT, although SAT is also not really predictable, it's like the most well understood fragment. So many people they still move to propositional logic encodings if they can. Sometimes you can't. So for example, if we wanted to, I don't know, scale up the number of houses, then the integer one would probably be the easiest, right? But yeah, this really depends on the case that you have, and I wouldn't rule out any of these encodings in any, let's say, real verification tool. So you might see the Boolean encoding, you might see the integer-based one, and you might see the data type-based one. And it's good to know all of these encodings and to know what are the, well, benefits of them. And I think that, yeah, you will see for task 3, where you have to encode this PC configuration, that, yeah, you can either use the Boolean one or the data type one, and you definitely need integers anyways, because you have to calculate some sums and stuff like that. But yeah, there are many encodings, and usually that's also why we didn't really want to restrict the way that you encode it. So for some of the tasks, we gave you the variables that you have to use, but for this PC configuration thing, we didn't give you the variables because we want you to come up with a nice encoding that works for you. Yeah. Okay. Yeah. Now, if we can do so many nice things, what about stuff which is really difficult? Anybody heard about RSA encryption? Some public key encryption where you don't have to have a pre-shared secret. You just share some public key. The public key is used to encrypt something. Then you share this message, and only the person whose public key you used can actually decrypt the message. So it's, well, yeah, quite popular for online communication, these asymmetric encryptions, because then you don't have to, well, exchange secrets over channels that might not be secure. Okay, so maybe you looked into this. How do you actually break the RSA encryption scheme? So the public key and the private key, they are two very, very large prime numbers. And well, sorry, the private key one. I think maybe the public key is the multiplication of them. And actually, to break RSA, it's enough if you can factor the, well, public key. So if you can factor a number and you find the two components that are prime numbers and that together multiplied give you the public key, then you can decrypt the message, right? So if somebody could factor those numbers, could find those factors, then this would be very bad for, well, almost anything on the internet. And that's also what people are expecting, that quantum computers can do this, right? So why not try it with SMT solvers, right? Why not? Maybe they can also do it. So how would we actually, yeah, try to break RSA? Oh, sorry, I need to use the other one. Do I have the, well, yeah, so basically, what do we need to do? We need a number, which is this compound number, and then we want P and Q, which are the factors of this number. We know they have to be positive, and they can't be 1, right? Because if one of them is 1, then the other one is that large number, right? And we didn't really do anything. So how do we... I don't have a link for this. Well, I didn't put a link here. Well, but basically, this would be some solution. We can get some big prime numbers, and then we can simply state that the multiplication of our P and Q is this number, and then the model will have assignments to P and Q. So these are the factors, right? If you multiply this number with this number, you end up with that number, right? So we kind of, yeah, did we break this cryptography scheme? Let's see how many bits do we want to take? I don't know. Let's generate some RSA for 16 bits. So let's put this here. Very small numbers, right? But yeah, we broke it. Factor to test. Okay, so we need to give it one of the factors that we found. Well, 103. Let's yeah, great. Okay, so now, well, 16 bits is, I don't know. Do you know what's a realistic RSA key size? Well, 16 is not. Let's try 32. You see the numbers grow, right? Well, the bits grow, the numbers grow, so let's see. Okay, process time about after 5 seconds. Yeah, so I mean, this was a 32-bit number. So for a long time ago, traditionally it was 1024 bits, but actually people are now at something like yeah, what is 48? Like 2048 bits. Yeah, and if we already timed out for 32 bits, you can imagine that our solver has no chance of ever breaking any reasonable size security key, right? So the expression here of the problem formulation is exactly the same. The only thing is that the data that we're using grows. And then basically, yeah, we can't handle it anymore, or the SMT solver can't handle it anymore. So the only thing we really changed was this small parameter, but yeah, we have a timeout of 5 seconds and it couldn't even compute this 32-bit number, right? So yeah, this thing is not a tool to break RSA, and usually computationally very difficult problems, they remain computationally very difficult. The SMT solver just gives you maybe a uniform, nice way to specify what is it that you actually want to be solved. So here it's very, very easy to specify, well, we want to factor these numbers. And that's like one of the most easiest formulations of, I want the prime factors of this number. But, well, simply, if a problem is really difficult, then the SMT solver will either time out, or if it goes into the area of undecidability, if you use a theory that has an undecidable fragment, then it will simply tell you in some cases that it doesn't know. So it says the result is unknown, I give up. This is also what can happen. Okay, so this is, well, another application, but that's not, let's say, a successful application for SMT solvers. So let's look at some other ones. Let's look at the more, so I think this is the area of program verification. This is an area where things like SMT solvers really started out and were used a lot, also by Microsoft Research. I think they started with program verification. They wanted to do stuff like termination analysis or heap memory analysis, or simply program contracts. So it's very difficult to say when is a program correct. So there are some ways to address this. One is contract-based verification. So you basically annotate a contract on your program and you say, this is how my program will behave. So this contract is then written in some logic that is, let's say, easy to understand. And this contract will hold, or is supposed to hold, for the very complex program that you're going to execute. And then you can check whether this program might really satisfy this contract. And usually you also require that the program terminates, right? Because otherwise you can't prove anything about the output of the program. And then if you remember this issue of undecidability, so any programming language that is Turing complete, so any programming language that we're using, you can't show that it terminates. So we're immediately in this area of, again, undecidability, but still finding, let's say, proofs or finding issues like counterexamples where you can say, well, this contract is actually being violated. This is still very, very helpful. So that's why people did this. And it's about real programs. So the stuff that really runs on real computers. So that's why it's such an attractive area, because it will help tons of people if you can find out stuff about programs and violations of contracts. But it requires you to write some contracts. So I'm not sure how many of you have heard about pre and post conditions. Pre and post conditions? So this is the contract that we're going to write. We're going to write a precondition that says whenever you call this piece of code and this precondition is satisfied, then this piece of code will ensure that the post condition is satisfied. Yeah. So first, we need to define what are the needed variables. This usually relates to what are the possible inputs. We need to talk about these inputs in the precondition, and what are the possible outputs. So we usually need to encode also the outputs as variables, and we need to talk about this in the post condition. Why would we need preconditions? isn't okay. So let's come up with some conditions. So let's take as an example very simple stuff that everybody knows, not simple, but very common, is sorting a list, right? What would be a possible post condition? What would you require from the list that is returned by your sorting algorithm? That it is sorted so that the elements are in ascending order, right? Anything else? Just sorted, that's it? Then you're happy? What is the time complexity of sorting algorithms? It depends which one you use, yes. So I think the best one is something like n log n, right? Quicksort. If all you want is that you get a sorted list, I can implement a sorting algorithm in constant time. I can return an empty list. The empty list is sorted. Or I can return the list which has two elements, 1 and 2. That is sorted, right? So maybe your post condition is not strong enough to actually make the contract meaningful, right? Because I can easily satisfy this contract that I give you a sorted list, but it could be a list that I had, I don't know, 10 years ago, and I'm always returning the same list, right? So you probably want something a bit more complicated as your post condition. So your post condition usually also has to refer to your input, right? You want that the elements in the list are also the elements that were in the list that you gave me when you called my sorting algorithm, right? So there's a bit more tricky stuff going on. But then why would we need preconditions? Okay, so the precondition would usually mean that if the precondition, so the precondition is what I require from the input that you give me. And if you don't satisfy my precondition, then I cannot satisfy my postcondition. Okay, so let's say I have some very fancy algorithm that works really, really fast on lists, but only if they don't have duplicate elements, right? Or only if they don't have null values in there, because then my algorithm would crash. Then I could say my precondition is that your list doesn't have null values, or that your list doesn't have duplicates. And only then I guarantee you that I work really fast and that I work really correct. In cases where there might be null values, I might work incorrectly. I might give you, I don't know, everything only until the first null value and then I stop, right? So this is why we have those preconditions, because sometimes it's simply impossible or not convenient to handle all kinds of cases in the program code. So there are other things like you can imagine you want to write to a file. There would usually be a precondition that says, well, this file actually has been opened, and it has been opened with write access. Because if you have opened the file but only with read access, you can't expect the write method to work on that file, right? It will maybe throw an exception. So because you didn't satisfy the precondition. So the preconditions are really important for those contracts, because, for example, for the write operation, you would expect that if you give it some, I don't know, byte buffer, that it writes that to a file. But it can only guarantee this if you opened the file with write access. Because if you try to write to some file that you even maybe don't have access to, that's not going to work. So that's why we have those pre and post conditions. And then the way that we handle the post condition is we're going to encode the precondition, and then we're going to negate the post condition. Why do we negate the post condition? So we're going to have the precondition. We're saying all the models that we're looking for, they will satisfy the precondition, because otherwise we don't really care, right? We don't need to verify anything. Then we encode the behavior of the program, and then we have the negation of the post condition. So what am I going to get as a model that satisfies this stuff. It's a model that satisfies the precondition, but does not satisfy the post condition. And if it doesn't satisfy the post condition, but I have encoded the program correctly, then this means that my program has a bug. So actually what I'm trying to find is there any way that my program would ever violate the post condition if the precondition is satisfied? And if I find an example here, then I know I have a bug in my program. And if I don't find an example here, and it says there exists no example, then I know that my program is correct, and it will always satisfy the post condition as long as somebody makes sure that the precondition is satisfied. Okay, so yeah. Now let's try to look at a program like this. Let's say a very simple program. We only have some assignments and some arithmetic. So we have a equals y plus x, b equals a minus 1, a equals y plus b, and so on. What would happen if we try to encode this in SMT? We can encode this, right? There's even a simpler one. Okay, well, let's maybe encode, or let's see what happens if we encode something like this and this one. Right now, this is a program, right? Or I think there's a simpler one. Yeah, let's do this one. This is a swap. You want to swap the value of some variables. And it does that by using some arithmetic to swap them, right? You could also have, usually when you swap variables, you have to have one variable where you store the first value in so that you can then override the other variable. Here is actually maybe a program that works to swap integers, right? We don't know, not sure. Maybe it does work. So let's try to encode this. No. Where's the here? Okay, so what do we need to encode this? We need some variables, right? What variables do we have? X and Y. So why does it put the star? Okay, back to German. Declare const x of type int, right? And then we want a y of type int. Okay, and then we have this assignment here: x equals x plus y. X, so we have equals x plus xy. Yeah. Then we have y equals, well, yeah, x minus y, right? And then we have x equals x minus y. Now, we didn't yet have any pre and post condition, right? If we just run this, what does it mean if we run this? Okay, let's give some concrete values. What should we give? Let's say we call this swap method. With x equals, I don't know, 5. And then, of course, we want to, well, see some difference. So let's call it with y equals 1. So if we call it with 5 and 1, or even with, I don't know, well, 2 and 1. Let's keep it very, very simple. And then if we run this, what are we going to do? What are we going to get? We're just executing the program, right? Oh, wait. Answered. We can't execute this program. Could you execute this program in a regular programming language? Yeah, right. You can just say, well, we can plug in the numbers. Let's plug in the numbers. And let's see, if we plug in these numbers, right, then x becomes x plus y, so x becomes 3, right? Then y becomes 3 minus 1, which is 2. Then 3 minus 2 is 1. So we have 2 and 1. That's exactly swapped, right? So, yeah, what's wrong? What is the value of this x? Well, okay, what's the value of this x? 2. What's the value of this x? 2. So we will find one model which assigns each variable a value. So the variable x, we know which value it's going to assign, right? It's going to assign 2. So we're actually asserting here we're basically asserting here 2 equals 2 plus 1. Doesn't look good, right? Something is wrong. Okay, so why is that? How can we do it here and not here? Because this is an assignment. This is an execution of a program that keeps track of the values of variables, and then it can assign between different lines. It can, of course, or even in the same line, it can assign different values. This is the x that we got as an input, but then this x is being assigned to this sum here. So even in the same line, those x's already have different values. But here in a formula, this doesn't work, right? That's a completely different world. So we have to solve this issue of keeping track of what did the assignment actually do. And this is what this single static assignment does. So the single static assignment makes sure that each variable is used exactly once. So you cannot reuse a variable. So whenever here this a, whenever you want to assign something to this a, you need to give it a fresh name. This is a1. And then you can use a1 down here. This is no longer, well, of course, this has to be the kind of the same a as this a1. And then you assign this to b, and b is now the b1. And this a here that you are assigning, that's a fresh a. That's not the same a. That's a new variable a. So this single static assignment does exactly this. It creates fresh variables for each assignment. So this way, you will not run into this issue that you're saying things that are logically incorrect, right? So here, if you have some original like that, then you would create a fresh variable for each. And then, of course, you have to keep track what was the last assignment to this variable. So this v here, which one are you going to use? Is it this variable? No, it has to be this variable because that's the last one that we assigned. So this means that this occurrence of v has to be the closest one that was in the previous execution. Now it gets a bit tricky when we have some branching here. So we have an if that if this condition p evaluates to true, then we're going to set v equals 4. Otherwise, we might set it to 6. So now this single static assignment has the problem that it's no longer a unique variable name. So now what we have to do is we have to continue computing with the possibilities that we had. So v5 that we use down here for this v, we can create a new v5, which is either v3 or v4, depending on this predicate p. So usually we would also have to drag this predicate p down here. We would have to evaluate again here this predicate p, and only then we have the value of v5 that we can use in this assignment. So single static assignment gives us this ability to then encode it with new variable names in the SMT solver, so that then we can read, well, what was actually the last assignment to these variables, and then we can actually implement or simulate programming where we can have fresh variables for, well, each line, maybe not really each line because only for each assignment, right? So it's a bit better than encoding each line in its own fresh variables, right? We only have to copy variables when we make a new assignment, so when we could have a different value. Okay, so we saw that basically for if statements, we have to keep track of the multiple possible values. What do we do for loops? A loop is like lots of if statements, right? So the condition is the loop condition. Do we do one more iteration or do we stop? So that's basically if I have a loop that executes 10 times, then how many fresh variables do I need for each assignment in this loop? Well, I also need those 10, right? Because if the assignment happens 10 times, I could have 10 possible different ones. And the execution, how many times the loop executes, I usually don't know this because it might depend on the input parameters, right? So how can we represent that? So we know if the loop is executed 10 times, we need 10 fresh variables. If it's only executed once, we only need one fresh variable. But we don't know in advance how many we need. So how do we do this? So the simple answer is we try to allocate enough variables so that we can hope that we capture all the interesting program behavior. What does it mean, capture all the interesting program behavior? So we're trying to find bugs, right? But we cannot have a growing number of loop iterations. So what we have to do is we have to actually unfold the loops into something like nested if statements. So you have like an if statement, if the condition of the loop is true, then continue like this. And if it's still true, continue like this. So you basically copy the body of the loop many, many times with nested if statements. Let's say you do this for maybe 10 times. And then you are guaranteeing that the SMT solver can analyze loop unrollings of depth 10. And the user will decide how many times do I want to unroll my loop. I think 10 is already a lot. So there are some programs that maybe only analyze loop unrolling of depth 2 because they say, well, if no bug appeared after unrolling the loop twice, hopefully nothing bad happens, but it doesn't guarantee it. So for loops, we do loop unrolling by basically copying the body of the loop and always having some if statements. And then we know how to do this single static assignment with these conditions, but it can get very expensive. So loops are always an issue, and we can't usually we cannot do a complete analysis that is correct with loops, but there are other tricks we can use with loops. Okay, but now let's look at the very simple ones here. How would we make a single static assignment out of this? We would, basically, wait, when is the lecture over? It's over, right? Yeah. Okay, so we will do this single static assignment on next week, because Friday we have the next exercise where you're going to again implement something automated using an SMT solver. So you always have this manual encoding, and then once you understood how to use SMT manually, you're going to use it programmatically to be able to automate this, right? Because in the end, you want to apply it to some software product or some problem that you have, and you don't want to be the one sitting there whenever, I don't know, your boss comes up with a new piece of code or a new idea that they have. Then you don't want to type up everything manually and encode it manually in SMT. You want to have a program that runs it and can give answers quickly, right? So yeah, that's why we are always doing this. First, we need to learn how to do it manually, and then once we know it, we're going to make it automated. Okay, good. So yeah, see you on Friday.